So the plan for today is to talk a bit more about A star. We'll talk about a somewhat more advanced property that A star has and prove it through a proof that I think is quite nice. And then we'll devote the rest of the lecture to motion planning and thinking about how A star in particular can be adapted in order to deal with some of these motion planning applications. So in order to define this really nice property of A star that I want to tell you about, we need just one definition. So we're going to say that the node X is surely expanded by A star. I'm going to focus on A star tree search for this for the next few slides. If the F value of X is at most the F value of T star, where T star is the optimal goal. So what's the idea here? What we're saying is, if some node has F value that's smaller than any goal, A star will expand it. At some point, it will be discovered by A star. It will be on the frontier, and it will be expanded before we get to the optimal goal that has a higher F value. Right? Because when we expand that goal, we're done. But this will actually be expanded before the goal. The only thing is, you might have some nodes that have the same F value as the goal, and then it really depends on tie breaking. Right? So those nodes may not be expanded, may or may not be expanded by A star, depending on tie breaking. But the nodes that have a strictly smaller F value than any goal would definitely be expanded by A star, and then we say that those nodes are surely expanded. So, essentially what we're trying to think about is how much work A star will do. And we're saying, well, it will at least have to expand all of these nodes that have this property. So that sort of gives us a pretty good idea of how much work A star will do. We don't really know about the ones that depend on tie breaking, but this is a pretty good estimate. And the claim is going to be that A star is what's called optimally efficient. So this can get a bit confusing. What we talked about last time was A star finds the optimal path. Okay, so we call this just being optimal. This is a term, different terminology that some people use, optimally efficient, which means not only does it find the optimal solution, it does so by looking at the minimum number of nodes in a sense. Okay, so the exact statement is the following. Any algorithm that is optimal given a consistent heuristic, so the only information you're given is a heuristic, heuristic values, and you know that it's consistent, will expand whenever given actually an instance with a consistent heuristic, all nodes surely expanded by A star. Or in other words, what this is saying is in order to guarantee optimality when you're given a consistent heuristic, we actually have to expand all of the nodes that are expanded by A star. So A star, in a sense, does the minimum amount of work needed to guarantee optimality when given a consistent heuristic. Okay, that's the idea. So is the idea clear? Now, this theorem is from a Journal of the ACM paper 1985 by Judea Pearl and Rina Dechtel. So Judea Pearl is a Turing Award winner at UCLA. Rina is a professor at UC Irvine. There are many, many subtleties in this theorem and proof. Actually, every time I look at my slides, I find another subtlety. So hopefully I found all of them, but we may find some new ones online. If you look at the paper, you'll see the proof is quite different. Even the statement of the theorem and the proof are quite different. So I checked this a few weeks ago with Rina, and it seems to check out. But again, there are many, many subtleties here. So definitely let me know if you see anything suspicious, and we'll try to work it out. Okay, so I'm going to prove this theorem to you. And I'm going to sort of gloss over the subtleties, but again, if you spot them, please feel free to bring it up. Okay, so again, what we want to prove is that we have that in every instance, in every search problem, every node that is surely expanded by A star will be expanded by any algorithm that guarantees to us to be optimal when the given information is a consistent heuristic. So let's say that we have some instance, some search problem that we call I, with a graph G and a consistent heuristic H. What do I mean by a graph G? So this is the graph of the search problem. So it basically says, here's the node S, And then, from the node S, you can take all kinds of actions, and you can get to other states, and then there are other actions, and each of them has cost. So this graph is the graph that describes the search problem. Okay, that's important. It's not the graph, the tree that's formed by A star. This is the search problem itself. And let's say, by contradiction, that there is a node X that is surely expanded by A star. We actually can be even positive here. So what I want to argue is, I just want to show you that X will be expanded by some alternative optimal B, algorithm B, where B is guaranteed to be optimal given a consistent heuristic. So what we said is, because X is surely optimal, surely expanded, just going back to the definition, so that says that the F value of X is at most the F value of the optimal goal, which I'm going to denote by C star. Okay, so this is just saying, X, just a definition of surely expanded. Now we're looking at this other algorithm B, so let's assume that it does not expand node X. Right, and what we want to do is reach a contradiction. So I'm going to do the following thing. I'm taking my graph G, and I'm going to create a new graph. I'm going to augment my search problem by adding a new node and a new edge. Okay, so specifically what I'll do is, I'm going to add a new node T. Right, so this was my original graph that had the node X, which is the special one that is not expanded by B, but surely expanded by A star. And I'm adding a new node T, which is going to be a new goal. And I'm going to design this instance in a way that the new goal will actually be the optimal goal on the new graph. And the weight, the cost of the edge between X and T is going to be H of X for the given heuristic function H, which I know is consistent. Okay, so the only thing I did was I said we had a graph. There was the special node X that was surely expanded by A star, not expanded by B. Let's augment the graph by adding a new node T and adding this edge with weight H of X. In addition, I want to define a heuristic function for this new instance. So the new heuristic function H prime is going to be exactly the same as the given consistent heuristic function H. And I just need to define it on the new node T. So of course, H prime of T will be 0. Yeah?
Isn't H of X also 0?
No, H of X was, it wasn't 0 because it's not going to be a goal, right? Because it's not the optimal goal.
It's not the goal in the original.
No, because otherwise it can't have lower F value than the optimal goal. Right, so we know that H is not going to be 0. That's a good point. So X, we can prove pretty easily cannot be a goal. Therefore, H of X is not 0. Okay, but we do define H prime of T to be 0. Cool. So what I want to argue is that this new function H prime is a consistent heuristic on the new instance. And the reason I want to do this, like why will this be important, is that my strategy here is to say on the new instance, the algorithm B will actually not be optimal. It will not be able to find the optimal goal on the new instance. What I assumed about B is that whenever it's given a consistent heuristic, it has to be optimal. Okay, so in order for the strategy to work, I need to show that the new heuristic I defined, H prime, is still consistent. So why is it consistent? Here the proof is quite easy. So if you look at two nodes, a pair of nodes, so just to remind you what was the definition of consistency, we said for two nodes X and Y, we have that H of X is at most the actual cost in the problem of getting from X to Y plus H of Y. I'm not sure why this is so bright. Let me try to play with this a bit. Maybe I'll try switching.
There might be exposure controls of the actual underneath your.
Oh, all right. Let's see. Actually, last time when I switched to the laptop and back, it was better. Let me try this.
You can just raise this. Does this move?
Oh, maybe. Oh, good. Excellent. Okay, too much light. Great. Okay, so this is the definition of consistency. And what we want to show is that H prime is consistent. So again, for every pair of nodes that already appeared in the original instance, right, we know that H satisfies this property. H prime is exactly the same as H, so obviously this property is still satisfied. I mean, one thing to note is the cost of getting between these two nodes is going to be the same as before because the only edge we added is to this new node T. So what we get is for if X and Y were in the old instance, H is the same, H prime is the same as H, C is the same, and this H is also the same, so everything is the same. So the only thing to worry about is if we have a pair of nodes, one of which is the new node T. So let's look at such a pair. So of course, like in one direction, H prime of T is 0, so this inequality will hold. That's easy. But let's look at the other direction. So I want to show that H prime of Y is at most CYT plus H prime of T. Right, that's the only thing we need to show.
Why is H prime of T 0?
Because we define it that way. And so it's a goal. In general, we assume that goals have heuristic value 0. But in addition, we get to define H prime. So we defined H prime to be 0 on T. Okay, so I'm defining a new instance, and I get to define it any way I want. And what I said is, I'm defining this H prime. I have complete control over what it is. But I'm going to define it exactly the same as H on every other node, and I'll define it to be 0 on T. Okay? Okay, so let's see. So H prime of Y is the same as H of Y. That's how I defined it. Because H is consistent on pairs that were in the original instance, H of Y is at most CYX plus H of X. Okay, so this is because of the consistency of H on the old nodes. Now notice that to get to T, the only way to get to T is to get to X and then use the new edge. So CY of X plus H of X, which is the cost of the new edge, is exactly the cost of getting from Y to T. Right? You have to get to X and then use the new edge. So you have this equality. And because H prime is 0, this equals to CYT plus H prime of T. Okay, so the only thing we actually used here, other than just trivialities, is the consistency of H on the original instance, and the fact that we can only reach T through the node X through this new edge with weight H of X. Cool, so H prime is consistent. Now, one thing to notice is that, like I said, my strategy is to generate an instance with a better goal than before T. I want to make T a better goal than T star. And indeed, if you look at the cost of T, GT plus H prime of T, it's going to be, we need to get to X plus take this edge. And we said G of X plus H of X, because X is surely expanded by A star, that's less than the optimal cost C star. Right, so this is just what we said here. Okay, so this is really cool. This says the new goal T on the new instance actually has cost less than the previous optimal goal T star. So of course A star, which is going to be optimal with the consistent heuristic, will expand X like before. Then we'll discover this new goal T, and we'll expand it before T star, and we'll get a better solution. But here's the cool thing. So what about the algorithm B? For the algorithm B, the new instance looks exactly the same as the old instance, right? Because before it showed, it's sort of every time, creating expanding nodes, it chose to expand, some nodes until it got maybe discovered X, but it chose not to expand X. Without expanding X, you can't discover this new goal that we added, T. Right? That's really the crux of this proof. So this new instance, without expanding X, the only difference is this new edge and the new node T. But without expanding X, you don't see any difference. So to the algorithm B, the new instance looks exactly the same as the old one. And in addition, we've given it this consistent heuristic function H, which again looks exactly the same as before as long as you didn't discover T. So this means that algorithm B will not be optimal on this new instance, in contradiction to the assumption that it's always optimal given a consistent heuristic. Okay? Yeah, question.
How do we know that B will not expand X in the new algorithm?
So, I mean, I guess it's like not a super formal argument, but what I'm saying is, G is also an algorithm that, like A star, works by expanding nodes in some order. It has some search tree, and all of the input. So think about, like the pseudocode of algorithm B, right? So it starts expanding nodes, and every time asks, okay, what are my neighbors? What have I seen? What does H prime tell me? But if you didn't expand X and you never see T, right, the inputs that you get to the algorithm, like at every step, will be exactly the same. At every time, you get the same neighbors, you get the same value of the heuristic function, like everything looks exactly the same to you. So if you say, B is, just think about the pseudocode, and like it's making decisions at every point based on what it's seeing right now, what it will see at any point will be identical as long as it didn't expand X. There is maybe a point here where you could say, well, the algorithm doesn't look at the whole graph of the search problem directly. It sort of works in a way that is equivalent to A star in that way, right? Like expanding nodes, deciding which node to expand next. So you could say there is an implicit assumption here that B is sort of in the same very general framework as A star. But subject to that, I think this is like pretty intuitive. Yeah.
Are you assuming that the algorithm B is a kind of deterministic instead of randomized?
Yes. So definitely. I mean, the statement is B. Well, so I guess you can say if algorithm B is in the same framework, even if it's randomized, if it definitely doesn't expand X, then you will have the same result. It may be a bit more difficult to define such a framework formally, but I think it should be possible to prove a statement like that. So if you say the probability of expanding X was 0, I think the same thing should hold. Yeah.
So why you assume that T only has H with X?
Second?
So why you assume that X only T, the new goal T only has H with X?
So that's the way I construct. Why I define the weight of this edge to be H of X. So you're saying like the goal T, right? The cost. So the way I define it is the cost of getting to T from X is H of X, where H of X was given to me in the old instance. But that's how I get to define this, because I'm creating a new instance. I'm looking at the old one. H of X was given in the old instance. And now I'm saying I get to add this edge in order to create my new instance. Okay, so that's sort of the freedom I have because I'm the one generating the new instance.
So new instance is generated by X and new edge.
Yes. Yeah.
So is the optimality of an algorithm defined with respect to all instances?
Yeah, so that right. So that's the definition we used. In the paper in general, they talk about algorithms that are optimal on families of instances. It also depends on the heuristic function. But basically, we looked at this B belonged to the family of algorithms that formally it's called admissible on a set, which is a bit confusing with admissible heuristic. But it's like algorithms that would find the optimal solution in this case on any instance given any consistent heuristic.
But here you prove that if such an optimal algorithm exists, then A star would be optimal. Is that right?
No, what I'm proving is that such an algorithm would have to do at least as much work as A star in terms of expanding the nodes surely expanded by A star.
But what if it doesn't exist?
So definitely A star is such an algorithm. So I'm just saying like B is some algorithm that is optimal in every instance given a consistent heuristic. A star is such an algorithm. So this family is not empty. But what I'm saying is, maybe there are no other algorithms in this family, which is false. But this is saying like A star in this family does the least amount of work. Does that make sense? I just want to say like there's no other more clever algorithm that would give me the same optimality guarantee but would work less. Yeah.
So we are assuming that when we define the new goal T, the algorithm B is never going to explore X. And since the only connection to T is from X, it is never going to be able to reach T.
It won't even see T. Yeah, so it's not only about reaching it, it's not even going to see it.
Yeah.
Right.
So we have indirectly disproven the assumption that B is optimal.
Yes, exactly. So we're assuming to reach a contradiction that B is optimal. And then we're saying, oh, but but it's not on this instance. Right? Okay, so let's take other questions about this offline because we should move on. I just want to ask you guys one question at this point, and I'm really happy so many of you have followed because this is really a pretty deep question, and a very difficult question. So I would be very excited to see the correct answers to this question. Why does the proof fail if we replace consistent with admissible? Okay, so the claim was about given a consistent heuristic, what would happen? There are actually several things that fail. One of them is like super subtle, and I think one of them is not as subtle. So what do you think? Like, what would fail? So what I mean is, if I replaced this statement by admissible here and admissible here. So every mention of consistent I replaced by admissible. Any ideas? So think about the different steps of the proof.
It's not guaranteed to find the optimal solution with just an admissible.
No, so we're doing tree search, so it is. To give you a hint, it's on this slide. Yeah, Pradeep?
If we build H star in the same manner that we did here, I don't think H star would be admissible given that H star.
Perfect, excellent. Pradeep, right? Deepak, right, sorry. So Deepak is exactly right, that's really fantastic. So Deepak is saying the danger is if we start from an admissible and only admissible heuristic, and we do the same construction, H star won't necessarily be admissible. Okay, and then we won't reach a contradiction to the fact that with an admissible heuristic, B finds the optimal solution. So what's the intuition? Think about a situation like, you maybe had like X. So X, so this is X, it has an H value of 1. We added this new edge to T. So the edge would have cost 1. And maybe X had some neighbor, Y, with H equals 10. And the distance between Y to the optimal goal was 1,000,000. Right? So this is fine for admissibility. But now that we added T, right, Y is actually the H value at Y is actually overestimating. Right? When we added this new goal that's actually closer, the H value at Y is actually overestimating. Right? Whereas before with consistency, this kind of thing can't happen because if you have an edge of weight, I didn't say the weight, but let's say weight 1. If you have an edge of weight 1 here, the H value at Y can't be that high. Okay, so this is sort of the nice property of consistency that makes that construction work. And in fact, it's not only that this proof fails, the theorem is just not true when you only have an admissible heuristic. And I want to show you a counterexample. I think this is really cool. Again, it's like pretty subtle stuff, but I think really, really cool ideas. So let me show you why a counterexample to this theorem when we replace consistent with admissible. So here's the example. Okay, so we have, this is the graph that describes the search problem. And I'm going to define the following algorithm B. So B conducts exhaustive search over the whole search problem, except for expanding a special node called A. And then it expands A only if A still has the potential of leading to a cheaper solution based on the information you have at that point. So let's see what will happen, okay? First of all, the way I define the H values here, it's admissible, because here, this H value is very large, but here maybe there's like a very long path. Maybe there's even a goal in the end, but this is fine. Like even though this is large, you can't actually reach T from the node B. So this is okay. It's not consistent because there's an edge of weight 1 here, and this H value is only 1. But this is admissible. Now what will algorithm B do? So it expands S, it expands B, it expands C, it expands T, so discover T. And now it's asking itself, should I expand A? Like, does A have the potential to give me a cheaper solution than T? So it looks at its available information and says, hey, B has an H value of 20, and the heuristic is admissible. So I know that any path from B to a goal would have to be of length 20. In particular, the path would be cost 1 here, and then from A, it would have to have cost 19. Whereas the cost of T is 7. Right, so this is, I think this is really cool, I think, right? So it's saying, what do I mean by only if it has the potential? So this heuristic function is stupid and is not consistent. Like, it doesn't know itself that it's ridiculous to put an h value of 20 here. Sorry, an h value of 1 here, sorry, right? But because this is so high. But, however, because this is admissible and this is 20 and we know this underestimates, that gives us enough information to say there's no way that A will lead to a cheaper solution than what we already know. So algorithm B at this point would stop expanding, whereas A star would in fact expand A because it has such a low H value and keep expanding down here. Right, so the point is A is a node surely expanded by A star, but this bizarre, and because it's misled by the stupid heuristic function H, which is only admissible and not consistent. And the algorithm B does this weird calculation of saying, oh, do I have enough information? Oh, actually, yeah, because I know that H is admissible and I can do this calculation myself. So that's the example. I think this is pretty cool. I mean, the fact that, right, because it seems like, how would you even come up with such a counterexample? And this algorithm B is so weird, but it's actually so easy to analyze in this example. Yeah?
Wouldn't expand A was the value, because from acid expand, it has outgoing with ABC.
Yep.
Wouldn't it see that A as having 4? Like, why wouldn't it expand? Or why wouldn't it say actually the value for A should be 4?
So we're just talking about A star, right? So the value of A would be, it is 4 right
Well,
here.
the algorithm B, why does it not look at A and see, oh, it's actually 4, and then we would acknowledge that potentially be a cheaper solution?
So that's what A star is doing, right? So A star is saying the F value of A is 4. Therefore, it could potentially lead to a cheaper solution, so I should expand it and keep it going down.
So is B not? Because B sees A like on the frontier.
Yeah.
It's not expanding it, but it should see it on the frontier with a value 4, right? With potential 4.
So B, so B is not, I'm not sure what you mean by seeing it. So when we expand S, we add B with an F value of 21, and we add A with an F value of 4. And then A will have the smallest F value. That's the next node will expand. Like, it's just a node with the smallest F value. So A star, doesn't think too much except.
I mean, algorithm B. Why would it?
Oh, B. Okay. Yeah. So B, because B is smart, right? So it knows that H is an admissible heuristic. And under an admissible heuristic, if the cost of getting from B, like from B you can only get to A. If the cost of getting from B to a solution is 20, it must be the case that the cost of getting from A to a solution is at least 19. Right, because otherwise, if the cost of getting from A to a solution was 4, you could get from H to a solution with the cost of 5, but the H value is 20 and the heuristic is admissible. So
But I'm saying, doesn't S because S looked at B and then in algorithm B, S looked at B, added that.
Right.
But also should have looked at A, right? Or are we saying that it didn't?
Yeah, it did expand S, and it sees A on the frontier, right? It just knows, but it's looking at this whole graph basically, right? There is actually a subtlety here that just occurred to me regarding our framework for algorithms and what they're allowed to do, but let's leave that for later. Yeah.
So when we are talking that A star is optimal or efficient, so do we count the total number of nodes that we expand?
Yes.
But then, in this theorem, we're actually talking about only the surely expanded nodes.
Yes.
For example, if heuristic is exactly equal to the cost of the path to the goal, then there is no surely expanded vertices at all. And it could be the algorithm that works better than A star. Theoretically.
Sure, yeah, definitely. Okay. Yeah. So what we're saying is, tie breaking, we don't know, and you're absolutely right. When H is you could, well, in the case where H is, you're saying the case where H is exactly right. Yes. Then, no, so there, in that case, I think A star will actually just take the straight path to the goal.
Yeah, I mean, like in the theorem, we count only the
Yeah.
node that's surely expanded.
Yeah, no, I mean, yeah. So you can definitely build examples where A star, because of tie breaking, will go like in completely different directions. It won't happen under the heuristic function, which is like knows exactly what's going on, but it could happen under other consistent heuristic functions, and that's completely right. So it could like do a lot more work than another algorithm because of tie breaking issues. So this is just saying, up to tie breaking, it does the optimal thing. Cool. Let's move on to motion planning. This was fun, but took quite a bit of time. Great, so this is actually going to be the easier part of the lecture. We start from like the heavy, end of like the heavy A star stuff. This is going to be back to the basics in a sense. And I just want to tell you, it's going to be like a very, very quick, not even introduction, just like tasting like a few things in motion planning, just to show you like a few cool ideas and how they connect. So, motion planning in general is navigating between 2 points while avoiding obstacles. One application obviously is robotics, but actually we'll think a lot about 2D instances, so two-dimensional instances on the plane. So nice examples for that are like real-time strategy games like StarCraft, or things that I play more, which are like role-playing games, old ones like Baldur's Gate, or new ones like Dragon Age Inquisition, where you control some character and you have a group of lackeys who follow you. So they actually have to find their path, as they're following you around in mazes and stuff. Right, so these are like very common examples of pathfinding in 2 dimensions. So, one difficulty in this thing is that, we have to try to think about how we even apply the stuff we talked about to this kind of problem that is continuous. Right? That's one big obstacle. So the first approach would be, let's define a discrete grid. And we'll mark cells that intersect with obstacles as blocked. And then we'll just find a path through the centers of the remaining cells. So we think of the vertices of our search problem as the centers of the cells. And then, and then we just have like a regular search problem that we can apply A star or whatever to. And we can find a path through the centers of the unblocked cells. So what do you guys think? Like, will this find the optimal solution? And is it complete in the sense that it will always find a solution if there is one?
A huge graph if you do that.
Well, it depends on how fine you discretize the graph. But let's say like I choose some specific level of discretization which doesn't give me like a huge graph. Right, so I need to choose like the size of my cells. Mm-hmm.
Go back to the graph.
Okay, so is this optimal? Like, no, right? Why not?
You can discretize that fine.
Right. So because of the discretization, right? So I mean, my path is, my path is constrained to use centers of cells, and I could like cut corners and find a shorter path, like even in this example. What about complete? Like, will this, let's say I choose like a grid of some, some size. Yep.
I don't think it would be complete if you have a gap between your obstacles that's really small, smaller than your discretization. You might not have that. Your discretization might not represent that space.
Excellent. What's your name?
Sherman.
Sherman. So Sherman is saying, the problem is like it could be the case that I could pass between, I have some obstacle, some wall, and I could pass here, but this happens to be like within one cell, and then I say, okay, everything that intersects with an obstacle is blocked, so this whole cell is blocked, and there's no way through. Right, so that's the problem. So to deal with this problem, what we'll do is this idea of cell decomposition, also a very simple idea. So we'll distinguish between cells that are completely contained in obstacles and cells that only intersect obstacles. For cells that, if we couldn't find a path, we subdivide the mixed cells, so let's say divide them into 4 smaller cells. So in this example, if we can't go beyond like this 3x3 grid, initially there's no path between the blue points. But then because this whole cell is blocked, but when I subdivide it, I get these small cells and then I can find the path. Okay, so let's just refine the notion of completeness. We say that an algorithm is resolution complete when if a path exists, it finds it in finite time. If a path does not exist, it returns in finite time and says there is no path. Slightly subtle point. So we're going to assume for this that obstacles are closed sets, which means free space which is the complement of the obstacles, is an open set. That means that for every point in free space, you can find a ball around it. It could be a very small ball, but you can find a ball around it that is entirely in free space. Okay, that's what I mean by closed and open. So for every point in free space, you can find some ball of free space around it, maybe very small. So here's the first poll of 2 for today. So cell decomposition, that is satisfy A but not B, B but not A, both of these properties, or neither one. So I actually posted this poll last night, so you'll find it in yesterday's posts. Ten more seconds. Okay. Great, so we have a really nice majority for the right answer, which is A but not B. So let's try to think about this a bit. So why is it true? Why is A true? So why can we always find a path in finite time if one exists? Yeah, name?
John.
John, yeah.
I don't have a good intuition for why it works algorithmically, but it seems right because in synthetic topology, open sets represent semi-decidable properties.
Okay. That's not the argument I had in mind. Yeah, so okay, maybe, I don't know. Yeah.
You can always subdivide in some amount of like countably finite subdivisions until you actually find the path through the obstacles.
Okay, so that's the claim, but can you say like a bit more about why that would happen? Right, so the claim is like if A holds, then we can always subdivide enough until we find the path. I'm looking for like one more argument.
Yeah, I guess since the free space is an open set, there's always going to be some amount of discretization.
Excellent.
The free space.
Excellent. What's your name? Jonathan. Right, so what Jonathan is saying is, because free space is an open set, we're saying every point has like a ball around it. So if we, divide enough, we're always going to be like within, our cell, like for every point in the path, will be like within this point of free space. Right, so you can think about even every point separately. Eventually, like things will be small enough so that the point will be, the cell will be inside the ball of free space. Right?
But you cannot prove the discretization goal.
Oh, but things, I'm sort of giving you the instance, and there is some instance, so the obstacles are defined in advance. And so the balls, the instance defines the size of each ball for every point on the optimal path. Right, so you can't, like if you were creating the instance online, you could make things thinner and thinner, but you're not allowed to do that because you're giving me the instance in advance. Okay, so think about it a bit. Right, it's a subtle point, but it's true. So what about what's a really simple example for why B doesn't hold? Yeah.
Free space compact or?
So the free space is not compact because it's open.
It's open.
Yeah. So the
Infinity now, like large free space.
sorry. So let's say like the whole. So the whole thing, we're in a compact subset of Rn, of R2, let's say. Yeah, let's not get too bogged down in this detail. Yeah, okay, so what's an example? So let's say, but we are inside some square, okay, on the plane, and then we can't go beyond the square, okay? So what's an example for why B doesn't hold?
It'll just keep subdividing the cells forever.
So what would an obstacle, look like for that to happen?
Something completely surrounding the goal, like a donut with the goal inside.
Okay.
Or a wall that just divides the whole space in half.
Perfect. And how thin is the wall, right? So the idea is, let's just define, let's take our space, which is like a square, and what we'll do is we'll just add a wall, which is a line on the plane. So the line is sort of, has measure. Okay, forget. I'll not say that, but it's like very, very thin. And then we can keep dividing forever without ever like being small enough to fit inside this line.
So
right,
when it hits the wall, it's just gonna kind of almost stop. Just kind of algorithmically divide the cell, but
yeah. So it just says like if I couldn't find a path, I divide again. But it will never find a path because there's a wall, and it will never, and the cells will never fit inside this obstacle.
so is it like an infinite?
Yeah, it just keeps refining forever. Okay, cool. So.
Sorry, can you go back to the slide where the algorithm is defined? It is defined.
Yeah, where did I define it? Oh, sorry, this one. Yeah. So yeah, just like if no path is found, subdivide.
Dividing forever.
Yeah.
But how is the path defined?
Sorry. Oh, the path is between on the graph. So when we divide, we have the centers of cells. What's the question? Yeah. So we're just saying like it's a path on this graph where the vertices are the centers of cells, and you can go to an adjacent cell. Okay. Yeah.
So would this algorithm become resolution complete if we put a condition that divide only until the size of the cell is either equal to or greater than the smallest gap between two obstacles?
So yeah, I mean, in the example with the wall, the gap, by the gap between so you're saying like because the wall touches like the edges of, I don't think that will be complete, right? Like you could have a situation where you do divide that much, but still don't find a path even though there is one. That's a good idea. Yeah.
So in the real world where lines don't exist, so if you were to do something like a Z-space transform,
Yeah.
the line now has thickness,
Right.
it will.
Sure. Yeah, that will work. Yeah. And I guess and I guess what you're saying is, in practice, like this, this situation will not happen. Obstacles have some thickness, right? This is not a practical approach in general. Like in practice, we won't talk about this, but for this kind of thing, there are sampling-based approaches. So we're really like just talking about nice ideas here, not right now trying to get to a practical level. Okay. Okay. Cool. So. So let's just, right. So one issue is that, even if we did find the path, let's look at this example. So this is our obstacle. Maybe we subdivided up to some point, we got this grid. Our obstacle is blocking out some cells. This is the optimal path, if you don't go through blocked cells. But we're only allowed to use centers of cells, so this would be one optimal path, and this would be a second optimal path, okay, in this graph. So one thing we're worried about now, okay, and this will be like the main thing we'll be worried about, and this is like a more practical concern that really is something used in practice, is that this constraint of like we're not even giving an optimal solution because we're constrained to use the centers of cells, right? So this path and this path are both much longer than this path. So here's one idea. What we'll do is we'll run A star and find the optimal path in this graph defined by the centers of cells where you can go to an adjacent cell. But we'll use like an additional insight, which is that if x1 to xn is a valid path, and xk is visible from xj in the sense that there's an unobstructed line between them, there's like a line of sight between them, then x1 to xj, then jumping to xk and continuing on the old path is still a valid path. So the idea is we can basically cut corners by saying, okay, we have this path, but now it's doing these twists and turns. Maybe you can just take a shortcut and make it shorter than before. It's like a very simple idea, and the idea would be, let's do this as a post-processing step. So we run A star, we get the path, and then we check whether there are lines of sight that can actually make the path shorter. So this seems to work pretty well, right? Let's look at the example from before. We said, well, this was the optimal path. This was one optimal path through cell centers, the A star path. And now we're saying, hey, look, the last node on the path is actually visible from this node, so we can cut this entire corner and go like this, right? And then we avoid the obstacle, and this is like a much shorter path than we had before. So that's nice. Like that seems to work pretty well. Yeah.
Why not start with the visibility graph itself? Like you have your.
Yeah. So we haven't talked about the visibility graph yet. That's a great idea. So have you seen this before? The term visibility graph, because we will get to this at the end of like a long process. But it's a great idea, of course. Right. So I mean, the idea was basically let's define things based on the lines of sight. But for now, I want to like leave that aside for a while. Maybe just to answer your question very briefly, sometimes it's actually pretty difficult to compute these lines of sight. So in 2 dimensions, it's not hard. In higher dimensions, it can get pretty tricky. Okay, so there are many different approaches to pathfinding, and we're just talking about a few alternative ones. We'll definitely talk about that as well. Okay, so right, so this seems to work pretty well. Yeah.
How is this routing that is done in the reverse order from the goal to the?
I mean, I don't, yeah, you could do it that way. Let's not be formal about it because I'm showing right now that it fails pretty miserably. Okay, so let's just look at the same example, but the other optimal path. So here we can't actually do anything. Like there's no shortcuts because any shortcut that you try to do hits the obstacle. Okay, so this, it's a nice idea, but wouldn't work that well. So here's a cool idea, and again, we're really staying at the level of ideas. I'm not going to ask you to implement this. I just want to give you some ideas for what different solutions people have proposed, and just a bunch of nice ideas. So the idea is instead of first computing A star and then doing this post-processing, we'll hack the A star process itself in order to find opportunities to cut corners in advance. Okay, so what we'll do is, under standard A star, we say, we expand node X and we find node Y. We add it to the frontier with the G value being G of X plus the cost of getting from X to Y. And then we insert it with the estimate F of Y is this G plus, G of X plus the cost of getting from X to Y plus the H value of Y. So under this other variant that I want to tell you about called theta star, what we'll do is the following. So we first check whether the parent of X is visible from Y. Okay, so we're saying, we might add X as the parent of Y and do this. But if the parent of X is visible from Y, we can cut the corner already. Okay, so we'll just add the edge directly from the parent of X directly to Y instead of going through X. That's the idea. So what we do is if the parent of X is visible from Y, we insert Y. But the estimate is going to be the G of the parent of X plus the cost of getting directly from the parent of X to Y plus H of Y. Okay, so we just like at the point we insert Y, we already cut the corner. And now we have a better estimate for Y, and this guides the A star process. Okay, so I think that's a very simple, very cool idea. So I sort of ran it informally. I haven't checked this carefully, but I sort of ran it on this example. And I think it would give like this path. So the optimal path is the dashed one. I think it will give this one.
So is it done in iterations?
Yes. I mean, it's done the same as A star. Every time you have your frontier, you expand the node with the smallest F value. The only difference is in how you have your graph. So everything is the same. The only difference is how you compute the F value and how you compute the pointer of a node that you add. So it's not always from the node that from which it was discovered. It could be directly to the node before it.
No, I mean so if you take that as a target and you're seeing if I'm assuming that X is any point in the path, right? So
okay.
The parent of X is the node before that.
Not on the graph, in the A star search tree. Okay, so let's try to sort of run this very informally on this example. So what would happen is we start from this vertex, this blue vertex. We expand it, and we discover these 3 vertices. now we expand this vertex, or maybe this one. One of the vertices we discover is this one. But what's the f value that we have for it? The parent of x, so now this would be x, this would be y, but the parent of x, which is the blue node, is visible from y. So we'll just add, we'll say, okay, we'll just reach this node directly from this one, add the cost of this direct edge, and then add a pointer directly to the blue node. And now we're saying, okay, this node, let's expand it. So this is x now, and this is y. But now, hey, again, the parent of x, which is the blue node again, is visible from our current y. So again, we cut the corner and add the edge all the way back to the blue node. Okay, so we keep doing that. And like all of the nodes in this area, all of them, their parent is the blue node. So every time like you go back to the parent of the previous node, which goes all the way back to the blue node. So in this area, we're always like shortcutting back to the blue node, like that's going to be the parent. The only thing that's happening is once you start reaching this area, so you look at, for example, this is x, this is y, but now the parent of x, which is the blue node, is not visible from y anymore. So now you do the usual thing of like the parent of x would be this node. Okay, so that's sort of what's happening. So that's why you have a corner around this node. But from here, like all of these nodes would have visibility to this node, and we'll just have a direct path to the goal. Okay, so very informally, but this is sort of the idea for why we just need to turn one corner under theta star. So it does really well in this example. If I didn't do a calculation mistake here. So let's see what this looks like in practice. So this is a game that's close to my heart, Baldur's Gate. You guys are too young to have played it, I think. It was like in the mid-90s or something. It was like the role-playing game. So it's, I don't have a screenshot, but it's like a bunch of small characters like moving around, a lot of mazes. And people still use the mazes from Baldur's Gate as like a test bed for pathfinding algorithms. So this is a specific maze from the game. And so there's some discretization here. I think it was like 100 by 100 or something, or 1,000 by 1,000, whatever. And then A star finds the red path. So look at how the red path, what it looks like. Like it goes here. So think about it's like a character following you, right? And it sort of hits a wall, turns right, hits the other wall, goes in that direction. So this looks like a very unrealistic movement for like a character, even if it's like an orc or something. But it looks pretty bad. Whereas like theta star will find the blue path, which is pretty smooth. Right? So by looking at it, you can see like it's a much smoother motion path compared to the red thing. And this is nice because it's not only sort of finding shorter paths, they're also smoother. And people have sort of studied this, but it just gives much more realistic paths that look better like in a game. So that's pretty cool. Okay, so now I want to get to this whole issue of visibility graphs, and I want to get to it through this like really, really cool theorem. And again, it's not going to be super formal, but I think it's really nice because the ideas are very, very simple. So it's something that the kind of proof where like, behold the illustration, like that's the proof. So the idea is very simple. If we got into like topology and stuff and measure theory, it could get like hairy. But I think like the idea will be very clear. So now I want to talk about like a continuous space. So we're sort of going in the direction that was alluded to before, where we don't do any kind of discretization. We just work in the continuous space, and we just want to work with visibility in a sense. So we'll prove a theorem, and then we'll see how it plays a role in understanding what's the optimal thing to do in this space. And everything I'm saying is going to be in 2 dimensions, but it's also true in higher dimensions, or like the appropriate generalization. So let's define a polygonal path to be a sequence of connected straight lines. Okay, so it's like a path that consists of like these straight lines, like you turn corners and go like this. And an inner vertex of a polygonal path is a vertex that is not the beginning and end. So it starts at S, it ends at T, and every other corner that it turns is an inner vertex. Cool, so here's the theorem. Let's assume, like before, that we have closed polygonal obstacles. A caveat is that I'm going to allow you to touch the edges or the boundaries of the polygons. Okay, so you're allowed to walk on an edge and you're allowed to touch a vertex. So we have these closed polygonal obstacles. Then I claim that the shortest path between any 2 points S and T is a polygonal path whose inner vertices are vertices of obstacles. Okay, so A, it's a polygonal path. It never curved. It only has like straight lines, and it only turns at the vertices of the polygons. So all of its inner vertices, where it takes turns, are vertices of polygons. So it's basically like hitting all of the vertices, check, 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 until it reaches T. Like here's an example. If this is S and this is T, the shortest path would be to hit this vertex, make a slight turn, hit this vertex, turn, hit this one, and then go to T. Okay, and the claim is like the optimal path always looks like this. So, and like I said, the proof I think is, again, if you wanted it to be very detailed, it would be hairy, but the idea is extremely simple. So let's first prove that the shortest path is polygonal, that it only has, just straight lines, that it never curves. From the fact that, basically what we're saying is, let's suppose by contradiction that the path is curving somewhere, right? And so the path is curving here. And what I want to say is, well, because the obstacles, are defined by all of these straight lines, and I'm in this open set, I'm in like this free space, I can find a very small ball around the, in the place where it's curving, such that the whole ball is contained in free space. Okay, so think about it like even if the point P is on an edge, right? So maybe so the curvature would be like this, and I can, I can go like follow the curvature a bit, like just get off the edge and then find a small ball. Right? That's sort of the intuition. Yeah.
Assuming that there's a finite number of obstacles.
Yes. Yes. Good point. Yes. Okay, so the claim is, we can sort of follow in the curved area, just follow the curvature. You'll be able to find the point and like draw maybe a very small ball around that point. And what happens is the path enters this ball, goes through P and exits the other way, but sort of curving through, it sort of curves through. And of course, you could make it shorter by just shortcutting through this ball. So instead of curving, just take the straight line from the point of entry to the point of exit. Okay, so you found a shorter path, and that means that you couldn't have any place where the path is curvy. Okay? So this proves that the path has to be a polygonal path. It can only have, or proves that it can only have straight lines. So now we have to prove that it can only make turns. The inner vertices can only be vertices of polygons, and the argument is exactly the same. So we have the straight path now, but if you have like an inner vertex of the path in free space, then again, we draw a ball around it, and then you get the same situation. Like you have the point of entry, the point of exit, and you just shortcut this and get a shorter path. And even if the inner vertex is on an edge, you'll have the same situation. So it has to look, it might look something like this. So the ball is now not contained in free space. But again, it has to be a situation like this where you draw the ball, and the point of exit is basically lying on the edge here. So and the point of entry is outside of the edge. So we just do the shortcut and get a shorter path. Okay, so again, like this is not a formal proof by any means, but I think by staring at those illustrations, it's pretty intuitive what's going on, right? So
if you're going for the blue point on the left to the blue point on the right, after the first obstacle, if you just kind of make the line straight, wouldn't the path be shorter?
So you mean like the optimal path here would be to go to this vertex? Yeah, sure. Yeah, this is just some suboptimal path. Okay, I'm just finding like one point where it's suboptimal, basically. But you're right, like the rest of this path isn't optimal either. So you're right, like the optimal path would be to go like, I guess either 1, 2 or 1, 2 or something like that. Yeah. Okay, great. So here's a, yeah.
So the proof earlier holds no matter where the blue points are, the beginning of
Yes. So for any starting and end point, as long as you have a finite number of polygonal obstacles that are closed, blah, 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 you'll always have like, so what we're saying is like every inner vertex of the path is on a vertex of a polygon, but the first vertex and the last vertex are always S and T, like the blue points. Okay. Okay, so here's a question for those of you who have not heard the term visibility graph until we mentioned it like 20 minutes ago. It's basically the question is how you would define a visibility graph, okay? So how would you define a graph on which A star is optimal given this theorem? Okay, so the theorem told us that the optimal path always only has to use, is always like straight lines and always uses vertices of polygons as the inner vertices. So what I want you to do is tell me how you define a graph in a way that this theorem would imply that the optimal path on that graph is the optimal path overall of any path. Yeah.
Visibility graph where all the nodes are vertices of the polygons. And the start and end goal.
Excellent. And what do you mean? And what are the edges? Just to be explicit.
Basically the lines of sight. So.
Perfect. Perfect. And remind me what's your name?
Roger.
Roger. Right. So Roger is giving a perfect answer. What he's saying is, we'll define the following graph, and I actually have it here, of course. So the vertices are the vertices of the polygons as well as S and T. And you have an edge between two vertices if there's a line of sight between these two vertices.
You're missing one.
Am I? Like an edge? Let's see.
Very upper left.
So this here?
That one to the left.
And left upper.
Oh, right, this one, yes. Yeah, let me add it because I'll forget later. Okay, great. So yeah, hopefully I didn't forget anything else, but okay, well, I'll do due diligence after class. Yeah, so this is the visibility graph. So again, so the edges are when I have a line of sight between two vertices, I add an edge. And in the theorems, what did the theorem tell me, right? That the optimal path would only use the vertices of polygons as vertices, basically, of the path, and would only use like these, straight lines when you have a line of sight between the vertices. So that directly implies the optimal path on this graph would be the optimal path. Right. So that's, I think that's a really cool application of this like very intuitive theorem. So this, this theorem is quite powerful in saying this graph is optimal. So if you can actually build this graph and you run A star on this graph, you will find the absolutely optimal path. So of course, one thing I mentioned before is that it's in some cases it's hard to build this graph. In 2 dimensions, it's not that hard. So one problem is this line of sight checks. So you can do it with computer graphics kind of tools. But it gets harder in higher dimensions. The obstacles can be very complex. So it can be pretty tough. And I mentioned very briefly, there are many different approaches. Some approaches that try to make things easier in higher dimensions have to do with sampling points that you use as the vertices of your graph, basically. But we won't have time to talk about those approaches. So let me just ask you like a last poll about this graph. So this is a pretty mean poll. I'm really curious to see how you guys will do on this poll. This is actually a homework question that I like to give in the undergrad version of the course. And it's like, it's a question that people can think about for like an hour. And I'm giving it to you as a poll. And you'll have like, we have time, so let's take like 3 or 4 minutes. But let me explain what the question is to you. So, basically the question is how long, how many segments can the optimal path have, how many edges, as a function of the number of vertices in obstacles. So what I'm saying is the total number of vertices across all of our polygons is n, all of the obstacles, right? And the question is to bound how many edges can we have in the visibility graph, in the optimal path, in the visibility graph, in the worst case. Yeah, Priya?
We're assuming our heuristic is just the actual length of the...
Yeah, so we will find like the optimal path. So just think about like the optimal path, we will find it. So it's just about like how long does it have to be? Yeah. No. Yeah, so we're not assuming convexity of the polygons.
Are we going from point A to point B, or it could have many points?
What do you mean?
Is it just going from the start to end?
Oh, yeah, just between 2 given points. Yeah, so like the same setting we talked about so far. And I'm just asking, how many segments could we have in a path like this? In order to talk about it, I'm saying our parameter is the number of vertices in all polygons. How can we bound like the length as a function of this number of vertices? So what I mean here in the worst case is when the upper bound O of something would say in any example, that upper bound would hold. In order to say a lower bound would be some example, and the example has to be a function of n. It's basically a family of examples that depend on n, where the optimal path has that length. Okay, so in order to say in the worst case, the number is set of something, you have to give both an argument for why it can't be more than that, and an example where it's asymptotically that number. Okay? So these are like the two things you have to sort of do here.
So can you have to prove both bounds, but you will do at most?
Yeah, you have to prove both.
And the lower.
Yes. Yeah, so it's like two different homework, parts of a homework problem. So I think the upper bound argument is very simple. The lower bound argument, I'm looking for an example. It's a bit tricky, but I'm hoping that with 100 people and sort of crowdsourcing, there will be at least one person who will come up with an example. It was in the homework. Yes, you took it in? Yes. Okay, so let me open the poll, and let's say like we have like, I guess we still have 13 minutes. Let's take like 4 minutes to think about this, and I'll stop you in 4 minutes, and then we can talk about it.
Actually, I remember what that is. But I don't remember why you think it works.
If you don't know, just vote for Beats Me. Okay, excellent. Very good. So we have 2/3 for the right answer, which is order of n. So like I said, the upper bound, the argument for why it can't be more than order of n is quite simple. Would anybody like to say what it is? Like why the
can't just touch all of the
but I mean, I guess the concern is like touching the same vertex multiple times, right? Yeah. Right. So why? I mean, okay. Deepak. Yes, excellent. Right. So Deepak is saying, the reason is an optimal path will not have any reason to touch the same vertex more than once, right? Like that would mean you cycle back. Like there's no reason why that would be optimal. Okay, so here's the hard part. So can you give me an example, which would be like basically a family of examples for the lower bound? Yeah, in the back.
If you have a polygon that's very, very similar to a circle, and that's between you and null.
Oh, yeah, that's really nice. Actually, that's completely different than the example I had in mind, but I think it's true. That's a really. What's your name? Matthew. Yeah, I think that's a really nice idea. I believe it's true. So think about like, so basically like you have only one obstacle, and it's this polygon. The number of vertices equals n, but you just if I give you some n, so you draw this polygon. Whatever, it should be symmetric, but and then like you put S on one side and T on the opposite side. So the shortest path would touch like around half of the Yeah, I mean it would basically, I guess, go on the edges here, right? So it would basically turn with the angles of the polygon. That's a really nice example. Very good. Anybody have a different example?
You just put a set of squares in a row.
Excellent.
Point n squares with a point on one end and the other end.
Excellent. What's your name? Nikhil. Michael, okay, Michael, good. So Nikhil is saying, I think if I understand correctly, I was thinking of triangles, but it would be the same. So you're putting S here and T here, and then maybe something like this. So you have to go like this, and then, right, so you just put like squares, or it could be rectangles. I mean, I think something that's easier to draw is something like this. So S and T with triangles, and then you do something like this. Right, so each of these is a triangle. So for each of these obstacles, you have to you will touch one of its vertices, and then if it's triangles, the number of vertices that you touch is n over 3. Yeah.
Can you just put exactly identical squares in a straight line from each other? Like, is there some reason you have to angle them like this? Otherwise you can go.
Oh, so you just
Right, but the straight line will still touch the vertices.
no, but you're not making any. I mean, but you don't have inner vertices in your path, right?
Right.
Yeah, but that wasn't the question. The question was about like the number of inner vertices in your, or the number of edges in your, and yes, I don't want to count. I guess what I think you're saying is, I'll put all of them in a line. Oops, sorry. Well, we always can go back to the Stone Age. So are you thinking of like S and T, and then we just walk on this edge?
Right.
Yeah, but so this doesn't count from. I was thinking of like you want many segments in your path, where segment is like you take a turn basically. Right. So like the way I arrange the squares, it forces you to take turns, and triangles is even simpler. This wouldn't be exact.
Triangles have 3 vertices, right? So you just touch n.
You touch n over 3 vertices, which is the order of n. Yeah, right. So
You have n. Okay.
yeah, so we just wanted it in a symptotic bound. Yeah. Okay, very good. You guys are great, and we'll meet on Monday.
Verbal.